Okay, so it's time for the third lecture in this session, the last session here. The speaker is Joanna Symonowicz from Technische Universität Wien in Austria. Okay, please.
Hello. Do I need a microphone or actually the back row? Can you hear me?
You should use it in order for the online version.
Oh, okay. All right. So hello, everybody. Thank you so much for coming to my lecture. So I'm gonna talk about this device. It's actually the picture of what the title says. So it's a neural network image sensor that is ultra fast and it's based on 2D materials. So the idea was conceived by my professor Thomas Müller, and all the measurements and analysis was performed by Lukas Mennel. And I was a person who actually fabricated the device, so I actually made it. And then I made it using techniques developed by Stefan and Dimitri. And then Adai added some further conceptual work that was in supplementary information. All right, so maybe let's start with understanding the title, because I know it's a lot of buzzwords, it's a lot of words that sell, but it's actually all true. So it is a machine vision. So machine vision is basically AI with images. So it's trying to reproduce human eye with machines. And then because it's a machine vision, it's an image sensor. So it senses the image we project on it. And the material that senses the light projected onto it, it's 2D. It's only 4 nanometers thick, thus it's a 2D one. And then it's very fast, so it can recognize the images very, very fast, which I will show you later. Okay, so we understand almost all the words in a title, but what is a neural network? And I guess most of you know, but if there is this one single person who does not know, I'm gonna talk about it. And I think maybe even more experienced people might be interested which part of neural networks knowledge I'm talking about. Okay, machine learning. So difference between modern, like typical kind of problem-solving approach and machine learning approach. So traditionally, we have some data, we have some function. We say, for example, I don't know, we have some x's, please plot x squared, right? And then the computer does the calculations and we have some answer. But with machine learning, it's like I have, for example, one set of data, I have another set of data. Please find some patterns in it. So it's a computer that is actually making the rules. And you've probably seen a picture like this one, but the concept behind AI actually started by trying to reproduce human neurons. And it started in 50s, and I think the first person who built a neural network, a very simple one, who was recognizing, I think, squares and circles, was actually a psychologist or like neurobiologist, something to do with the brain, not the physicist, not the computer scientist. And so what does cell in our brain do? So it gets a signal from another cell, and some other cells, and depending on like the thickness of the channel, the connection, it gets it with a different weights, and then inside the cell, you can also add some bias, some other value. So, for example, so this is to make sure like this neuron will shoot, and then there is some function connected to it, and if it passes the certain threshold, it's activated with a certain weight, or it's not activated. And that's basically what happens in computers. It's the same scheme. So you have some inputs to your layers, which are parameters. I don't know, it can be estimate the price of the house based on, I don't know, location. It's location usually. Like the metrage, so how big the house is, whether it has a garden, etc. So these are parameters, and then you add different weights to it. And then in the node, you take the sum of the different parameters with their weights, you add a certain bias, and then this is the input to your activation function, which, as you can see, it's either should or should with a certain weight. You can add some, these are the different examples of activation functions. So for example, you have sigmoid, that is like a snake. So it's either 0 or you can shoot with a certain weight, but it will plateau at some point. You have relu, which is a very basic function. So it's either take the max of 0 or the input. And softmax, I had conceptual problems like putting it on the graph, but it's used for classification problems. So it will give you the probability of like which class my image belongs to. For example, you have some weird, I don't know, Pokemon, and it asks you whether it's a cat or a dog, and it will give you probability of how much of a cat and how much of the dog it is. Okay, so it's a small brick in a network, and after all, it's artificial neural networks. So you can see that each neuron is connected to a lot of other neurons, and then you have different layers, and you have this parameter. Well, so in each layer you have a smaller amount of nodes. You can go back to bigger amount of nodes, but you have dimensionality reduction. And after you reach the final output, in here you can, well, so you have to train the neural network. The whole point is to adjust these weights so you get the correct answers, and this is how the algorithm like learns what should be the correct answer, what are the rules. So in here, you have some loss function, which is basically you tell the neural network, okay, for example, I want this image to be a cat. So if it says it's a dog, you say, no, it's a cat. And then it sees the difference, and then it basically adjusts the weights. So, okay. So it's adjusts the weights so the answer is correct. But it can also be like some other parameters, a number of parameters. So you basically take the gradient over this function that tells you the difference between truth and the prediction, and you do a gradient descent. So you do take a gradient over each parameter separately. So it tells you how much of which parameter is telling you the truth and which is lying to you. So if the parameter is telling you more of the truth, you don't adjust the weight that much. But if it lies to you, you say, okay, just change it as much as you can. And we add this learning rate. So the gradient descent, so like adjusting what the correct answer should be, happens gradually. Because, for example, if we did the bigger step, maybe we would end up in like a local minimum and not in the global minima. So this is why we add this like parameter that tells you that the step should be small. Okay. So now modern computers are awful for AI. I think you knew it. So usually people are using graphic cards, right? GPUs, not CPUs. And they were, I think, introduced for video games. But they basically have a lot of different cores. So it's same calculations as on the normal computer, but a lot of calculations in parallel. But the problem remains the same. So in standard computers, in von Neumann computer architecture, you have logic unit and you have memory unit, and it's separated by a bus. Literal, like it's not a literal bus, but the signal goes back and forth, back and forth. And with AI, it's particularly problematic because if we look back, so this is basically matrix multiplication, so a lot of matrices. And in each step, you have to fetch weights from the logic unit. You have to multiply it. Then you have to go back. You have to change the weights, and then you have to fetch them again. And actually, this guy takes 80% of energy. And a lot of times people show you this graph when you have this, that we should have smaller transistors, twice as small transistors every year. So it's no longer a case because, well, first of all, our transistors are very small, so you can't really like go beyond the size of the atom. And the second one is that this guy produces a lot of heat, so you need ventilation, and ventilation is big, so you can't have very small devices anymore. So the trend, and basically the biggest problem in the development of hardware for AI, is basically to integrate this guy with this guy, so you don't have this bus. And it's once again inspired by brain, so you want to have some memory combined with logic unit all together. And there are a lot of different approaches, and we find a solution, one of the possible solutions. So in our approach, we basically we do this calculation in an analog form. So the matrix manipulations are done on the sensor, and it's analog. So the difference between digital and analog is that in analog you have continuous outputs and you perform calculations on analog, so continuous inputs, while digital it's 0, 1, 0, 1, so you have only two states. Okay, so how do we do it? So we focus on image processing, and image processing is particularly hard. I don't know if you worked with neural networks, but usually when you have an image, you don't just put an image of a cat, it's a lie. You make it black and white, then you put some filters, then you, I don't know, torture the cat one more time so it doesn't look like a cat, and only then a neural network understands, oh, it's a cat. So it takes time, right? And you have to take a picture, you have to manipulate it, so it's very, very long. So we wanted to do something that is very, very fast. And so in sensors, you have something called photoresponsivity. Very, very important word that I'm going to use a lot, so I need to learn how to say it. So it's basically, it tells you how much current you get per unit of power. So it's actually a very complex function that depends on like frequency of light, polarization, etc. And usually people are trying to make it independent of these values. So you have a sensor that will work in a lot of different conditions. But we took a different approach. So basically, you want to manipulate photoresponsivity so that you get the currents you want. So you can do multiplications that you want. Because if you look at it the other way, so the current is actually the inner product of responsivity matrix and the image. So image is basically like a spectrum, and it's different powers per different wavelengths. So it's so here you have a spectrum vector. You have here photoresponsivity matrix. So if you remember the equation for neural network, we start actually having something like that, right? We have some matrix inner product, and then you can add some bias to your output, right? You can add some current, and then you can make the output a bit more non-linear, and you actually get a neural network. You get a cell in the neural network. And also, currents are additive. We add them in parallel. So basically, you have a linear combination of matrices, and you basically get them for free. You don't have to do anything. You just measure current, and you get this manipulation. You just have to manipulate photoresistivity, and it's going to be a weight, right? You project some image, and then you basically have a cell in a neural network. So this is a basic concept. This is what this paper is about. Just this one equation, really. Okay, why is it cool? First of all, it's fast because you don't have to fetch you don't have to fetch weights. You just measure current, so it's very fast. It's much more energy efficient because, one more time, you don't have to fetch weights from the memory unit. And it's actually more sensitive because I don't know how familiar you are with electronics, but it's a bit like binning. So adding the output from different pixels. But in this case, we're adding the pixels that actually give the same response. So you're only magnifying the correct response, not just every response. which results in the loss of information. And of course, since you have like linear algebra here, you can use it to do a lot of algorithms. And actually, group is doing a lot of algorithms. But in here, we focus on artificial neural network. So we use it as a classifier and autoencoder. And don't worry if you don't know what it is. I'm going to tell you because we have plenty of time. So here is the concept implementation. So each pixel has a photoresponsivity. Photoresponsivity. That's a word. And it's current over power, as I mentioned before. And then you can divide each pixel into subpixels. So these subpixels will provide the weights of the R vector. It's much easier to say R vector than photoresponsivity, so I'll just say R vector. And then you connect them in parallel. So each time you have a subpixel of the same color, it's you connect it parallelly to other pixels. And I will show you why in a second. So you can either manipulate the R vector by putting some gate voltage, or you can just change the fill factor, which is basically telling you what is the ratio of real power produced by the cell. So, for example, you can manipulate the size of different pixels, and then you have different fill factors, and it will change your current. So basically, you can either manipulate the R vector, or you can manipulate the size of a cell, and this is how you can get different weights of your neural network. Okay, so in here, every node is like this pixel, and then each of these paths is this subpixel, right, that is connected together. You can see that, for example, here you have this connection, and yeah, this connection, it connects to the same output as this connection, right? They're all marked in blue. Okay, so now let's go to the hands-on example of implementation of this idea. So this is actually the sensor, and you can see it's very, very small. So it's this bar is 2 millimeters. It was very, very small. You can't really see the device with your own eyes. And this is important because usually when you do some optoelectronics, always they ask you whether like there is potential for miniaturization, because you know electronics tends to be small nowadays, so you can't come up with a transistor just like the one that Bell Labs came up with in 50s that was made of paper clips and was big and everybody was excited anyway. No. Now it has to be very small, very flat. Otherwise people are like, what is it? So it's small and it's flat and we're happy. So this part is a magnification of this part. So these lines are the connections to paths that are here and are like 1 millimeter small, but you can connect them with needles, so it's already big. But in here you have the whole structure, and you can see that we have 9 pixels, which might not be a lot, but it's a proof of concept paper. And you can already recognize, for example, these 3 letters if you shine like different laser intensities on different pixels. And you can see that each pixel is composed of 3 subpixels. And we used tungsten diselenide as a photoactive layer. I don't know, are you familiar with 2D materials at all? Anybody? Dima is, yeah. So usually when people have this discussion about the future of 2D materials, you know, there was very big hype on graphene, but we have some problems with proper fabrication of, you know, graphene layers that are infinitely smooth and perfect and don't have any grain boundaries. So nowadays when, well, at least 2 years ago, when people were discussing the future of 2D materials, it was mostly, well, the potential was in their beautiful, like, possibilities of bonding with light. So they have very strong light-matter interactions. For example, when you have some Raman spectroscopy, when you shoot laser, on something that is, I don't know, 1 nanometer. You don't really have a crystal structure, right? So you will not see any peaks. But with 2D materials, you see beautiful peaks that will saturate your spectroscope, which happened to me a lot of times because I was not careful. So they really bond with light very nicely. So this is why we use tungsten diselenite. And each subpixel is really a photodiode. So what a photodiode is, it will produce current when you shine light onto it. So it's like a solar cell, but it's, you know, it will give you some current because it sees light. So that's basically what photodiode is. So in here, you can see a proof of concept that it did indeed produce some current. But in here, the smaller graph, it's actually also very important because it tells you how R vector, which I cannot pronounce, photoresponsivity, can be modulated with a gate voltage. So you apply some voltage here, and it will change your responsivity to light in here in the material. And you can see we can modulate it quite a lot, which is nice. And this will be our core, so this is how we will be adjusting the weights in the neural network. Okay, so sadly, this was a video to show you how images are projected onto the chip, but it just changes the shape. But you can see that it's basically a polarized light with different shapes on it, achieved by the analyzer. And we project 3 different letters. It's N, V, and Z. And intensity is always kept constant. Okay, so I'm going to talk about fabrication because I did the fabrication, so it's something that I really, so this is my contribution to this paper. And I think the beauty of science lies in details, and everybody is always submitting the fabrication, but this is what takes months and a lot of frustration. So I think since I have 50 minutes, finally I have time to talk about fabrication. And the process was developed by Dima, who's sitting in the middle of this classroom. So he was kind to show me how to do it. So basically, you want to have some insulating and smooth surface, right? Just to start with, it cannot be bumpy. It can be very smooth because you're talking about like nanostructures here. And then you like spin coat a plastic onto it, and then you use e-beam lithography, which is basically you're drawing your patterns with electron beam on the plastic, and the plastic gets destroyed when the beam touches it. And this is how you can create structures like this one, right? Very complicated ones. So this is basically like you draw it with the electrical beam on the smooth substrate. And then basically whatever you drew gets destroyed, and then you can evaporate gold, and you will only get gold in the places where you didn't have a plastic. So can anybody tell me why we need titanium? So basically the gold will not stick to the silicon oxide, so this is why we always need the titanium substrate. It's not relevant, I'm just taking my time. Okay, next, we want to evaporate some insulator. We don't want to fry our flake, we want to gate it, which means basically we want to apply some voltage across an insulator so electrons feel that there is some potential behind the insulator, so they move, and we adjust like the R vector respectively, but we don't want the in connection with gold. So we put some oxide as an insulator, and it's done by atomic layer deposition, so you deposit it atom after atom very precisely. So it's a very smooth structure. But we also want some connections between upper and bottom electrodes. So this is a process developed by Dima. So once again, plastic is your friend. You put some plastic layer, and then once again, you draw with electrical beam your pattern where you want the connections to be. And then you edge them with KOH, solution with water. So you have some connection, you don't have oxide here. And then it was actually one of the hardest parts. So you need to get tungsten diselenite, onto the specific place. But at first you have to find it. So there are different ways of getting to the materials. One is like basically baking it and creating layers. So it's CVD. But you can also take the crystal and you can take the scotch tape and you can, destroy the crystal, and then you have very flat surfaces. And actually the second method gives you higher quality crystals, because the ones that are CVD grown, they usually have like a lot of grain boundaries and maybe second phases. So this is much cleaner. So this is what we did. We took a scotch tape and we exfoliated the flake. And later we basically like stuck it to the plastic. We moved it, and then it was a viscoelastic material. So basically, when you want to pick it up, you do it very fast. But when you want to put it down, you do it infinitely slowly. So later you have to infinitely slowly put it down in the place where you want your flake to be. And then you want to get rid of part of the flake that is not needed, because we only want the flakes where the subpixels are. So once again, plastic is our friend. We put the plastic, but now we basically get rid, once again with electrical beam lithography, we get rid of the plastic where we don't want the flakes to be. We leave the protectional cover, and then we etch it. We don't etch it for too long, because if you etch it for too long, your flake is gonna be gone. And it happened a lot of times during this fabrication. But finally we got to a point when you evaporate the top electrodes once again, and there you have your device after 3 months of work or so. So how good was the device? Actually, out of 27 subpixels, one didn't work because of some connection, or we don't know why. And then you can see that these curves are not exactly the same. So for example, I don't know, this one is slightly different than this one, right? In general, they are very similar because they were extracted from the same crystal. But with 2D materials, the problem is, well, basically its property depends much on where you put it. So if there was any dust, any imperfection, it did change the responsibility right away. But we have the detector uniformity of precisely 0.2 variance. Well, not variance, but standard deviation, because variance is the square of a standard deviation. And then we did some computer simulations to understand like how it's gonna diminish our performance. So you can see that if you have photoresponsivity deviation of 0.2, the accuracy will fall by by 2%, so not that much. And also, if you simulate the amount of failed pixels with 1 pixel, it doesn't make that much of a difference. And indeed, this is what we noticed, that still accuracy was very high, and even with 1 pixel destroyed, subpixel destroyed, it was still okay. And this is what happens to a human brain, actually. Don't try it at home, but if you destroy parts of your brain, after some time, other part of your brain will take over the functions. Okay, so this is a comparison between digital and analog implementations. So analog is basically our chip, digital is the computer. And this graph, so this is for these 3 letters that I showed before, and it shows you how fast it learns. So epoch is like a set of learning data after which the weights are adjusted. So you can see that depending on how much noise we got on the input, we didn't train the neural network on the perfect data set, because then it would not understand like any noise in the output. So you have to add some noise to the input when you train the neural network. And you can see that the training was slower when there was more noise, of course, understandably. And you can see that the dotted line is how fast the actual computer was learning, and the solid line is our image sensor, and there is not much of a difference. Always the computer was slightly better, but not that much better, especially when you look at the optimization of the loss function. It's almost the same. And actually, here is a nice summary that basically you will have some standard deviation with your photoresponsibilities with the analog device, but you can see that the difference won't be that big. It will be on the order of 0.5%. So basically, we did something that is as good as a computer. And this was actually the problem with analogs. I don't know if you know, but the first computers were analog, but they needed very, very big precision. And this is how they ended, because such precision could not have been achieved. But in this case, it's very easy precision. We did it with our hands. It doesn't require a very, very high precision. So it seems to be the future, if you ask me. So now let's go to actual implementation. So what we did, we used the neural network as a classifier. So what is a classifier? So it classifies images. That's how easy how it is. So we have some noisy input, and the neural network tells you, okay, I think it's N. It won't show you the image. It just says, okay, it will point out to the channel that says it's N. So we partly did it on the chip, and we partly did it in our PC. So this part is actually our sensor of the neural network. And in here in blue are the parts of the training algorithm that were performed on the chip. And white ones are what was happening in the computer. So here is the scheme. Basically, the chip was connected to the computer, and some laser was put onto the to project images. So here are some details for people who are into AI training. It's very, very basic. So initial weights were random from a normal distribution, so we took just random numbers. Then softmax function was used as activation function. As I said, it will give you the probability for the classification, which category it is. We used cross entropy for the loss function. So it's the comparison that includes a log. And then we chose the learning rate of 0.1, and we projected 20 images per one learning epoch. So epoch is when you show a set of images and later you adjust the weights after these 20 images each time. Okay, so this is how the training data looked like. So as I said, we added some noise at first. Well, it was 3 independent trainings. So once it was 0.1, 0.3, 0.4, you see it gets more messy. But the classifier managed in each time. So this is the initial state of responsivities in the subpixels. And this is the final state. So this is what the training decided that our responsivities should be on each subpixel. And you can see that, once again, I showed this picture in a different variation, but basically when we add more noise, the output is going to be, the accuracy of classification is going to be slightly lower, but it's still quite nice. It's over 80%. I think, I don't know exactly what's the accuracy, but I know that in 2010 it was like 95% for neural networks to recognize images. So it's basically very comparable. And yeah, here you can see after each epoch, the loss function was minimized. So once again, it was slower when you have more noise. So this is a representation of this. So at first you had some normal distribution, and later the weights were spread according to the training algorithm. Okay, so here is how it works. So you project any of this letter. So for example, in here we projected letter N, and you can see after, this is training, right? So after like 10 training cycles, you can see that when we project N, the current connected with the channel N will be higher and will be non-zero actually. And in here, the same, but for V and for Z, right? And apparently, the sensor had problem with Z. So Z is not a nice letter, but it was quite good with N and V. Obviously, like you can see that the performance was good after a few epochs as well for Z. Okay, so now autoencoder. So this is actually even cooler. because you take an image and you encode it in a binary code, which is great because in here you have analog to digital converter, right? So you don't have to take the image, put masks, make, I don't know, giraffe, black and white, and then make it, butcher it basically so the computer understands it. But you get the binary representation of the image right away, and you get it ultra fast, as our title tells you. So you code it in some weird code, but then the computer from this weird code is able to reproduce it. So this is what happened. And once again, these are some details for neural network people. So once again, the initial weights, so for the responsibilities, were normally distributed. We used sigmoid for both code and output neurons. So we had to train both these guys and these guys. And then the loss function was basically a mean square difference between original and reconstructed image. And backpropagation was implemented in the same way. So once again, 20 pictures per learning epoch, and then the learning rate was 0.1. And these are pictures. I put them because it's just so nice. It looks so nice. And in this, for autoencoder, we used standard deviation of 1.5. But later, after we trained it, it understood images that were even noisier, which I'm going to show. So this is cool because in here, it's a video that works. So in here, you can see how the weights were changing after each epoch, right? So this was normally distributed. This was just set to 0. And you see that with each epoch number, they are kind of like stabilizing. So these are the final weights that we got. So it's just on this graph because I think it's important to understand where we are on the graph. So these weights, these weights are here. And then to give you the further understanding, so each pixel, right, has these 3 connections to 3 outputs. So this pixel is this pixel, this pixel is this pixel, this pixel is this pixel. But in here, you have summation of currents. So you have values of the summation of photoresponsibility and the spectrum. And later you apply some nonlinearity, so you apply the activation function. So basically it's either 0 if the sum was negative, or 1 if the sum was positive. So in here you have basically compressed representation, so you have binary representation ready for your computer to be used right down on the spot. Very nice. And based on this representation, the computer is able to reconstruct the image. Okay, so in here you can see weird thing happened around the 8th epoch, but the loss function stabilized. And we, once again, this is what the video showed, that at first we had like normal distribution, but later, well, or basically distributed around 0, but also normally. And then later it did change. The machine like chose which responsibilities it wants. So you can see that we projected a lot of different letters with higher noise. And look at this reconstruction. It's pretty, it's beautiful. It understands. It understands better than me because I had problems understanding what it is, but it knows it's V. Okay, so why it's ultra fast? So the only limit to how fast the correct channel is chosen when we project the letter onto it is a generation of electrons when we shine light onto a material. So in this case, it's 50 nanometers, but 50 nanometers was basically the speed at which we were projecting images with a laser. So we had a chopper that was like chopping off the laser, and basically it's the resolution of how fast for the period that a laser was touching the chip and not the chip itself. So in here it's 15 nanoseconds, but it can be on the order of picoseconds. So it's much better than taking a picture once again, changing the color of your giraffe, putting some filters onto it, etc. So it's right on the spot. In picoseconds, you get the conversion of image to a binary form that our computers understand. Okay, scalability. So I know it's 9 pixels, so it might not be very sexy, but it is because it has a potential of scalability, and I will show you that already some work has been done to scale it up. So one problem, how to utilize it commercially, would be that now we have to use computers to store the weights, but the weights can be also stored inside the photodetector. And you can use some ferroelectrics, or you can do some floating gate, and I'm gonna explain it in a second, so don't worry. You can add up the number of pixels, but it's straightforward. You just need more pixels, that's it. It's easy scalable. If you want more layers, where we already showed the layer where you have an image and you convert it into a digital form, and then you can add some memristors. So these are like transistors, but they remember their state, and you can do basic calculations on them, and it's already proved that you can do calculations on them. And then also we note, besides that the training can happen like off chip, and then you can understand which properties you have to have. You can do some simulations, and later you can adjust your fabrication process accordingly. Okay, so the problem with the fact that the photo detector did not remember its weights, so you can add a floating gate. So a floating gate will basically store its photoresponsivity after you switch off the gates. So in here you can see that some voltage was applied to the gate, and later the light was switched on, and you can see that it produces current of about negative 0.2. Later we switched off the light, it went back to 0, and then in here you don't apply any voltage to the gate, so it just remembers its state, because basically the electrons are stored here. And later it goes back to the photocurrent it produced before. In here, the light is slightly dimmer, so it understands it as well, so it's linearly proportional to the light. Then we switch it off, switch it on. Very nice. You can see that slightly this response is drifting away. And same here. And this is done for the opposite polarity of applying the gate voltage, so it behaves the same way. You can see here that it can go both ways. You can basically adjust the responsivity both to plus and minus, so it's very nice for the neural network. And once again, it just goes back to its previous state. Okay, favor work, because it's not the end. It was the end for me, because I left the group. But there were people in the group still working on it, and they did some amazing job that I thought it's worth mentioning. So for example, in here, Adai extended the previous idea, and he actually did a photodiode that is a memristor, so it does remember like how it was adjusted, so which gate voltage was applied to it, by basically storing current charge in this floating gate that is a clustered gold. And you can see that even though the current, you get less and less current produced after a certain amount of time, it is still much more that the dark current level. So in here you have 2 days. I don't know what happened after 2 days. Possibly it died, but it's still quite a lot for memristors. I don't know how familiar you are with memristors, but well, technically they should last for 10 years, but nobody can really reproduce the 10 years from one device to another. So already 2 days, it's quite good. And it also depends on like how you use the sensor. So you can, use it for an hour and then it's fine, right? Then it's already like the proof of concept is already there. You can add this gold layer, and then you can store charge. And in here, more pixels were added, but I believe there were some fabrication problems. So problem with 2D material is that already, like when I had to find a flake for the previous sensor, it was extremely big. So it was like 100 microns. But usually people like find flakes that are on the order of 10 microns. And if you have different flakes, there is a big chance they are not very uniform. So you have to come up with some other solution or grow perfect tungsten diselenite. Maybe somebody will be able to do it that will have the same optical properties on big areas. So in here, gallium arsenide was used. And what varied was we did not apply like gate voltages, and we did not change because I didn't do it. So they did not change responsivities, R vector, but they varied the fill factor, which was basically the size of subpixels. And they did it to match the patterns of more complicated letters. So you can see the letters are already, look more like letters, less like, I don't know, Mario game from 90s. And in here you have a classifier that is quite simple. So basically, if your pattern that you project matches with the fill factors, you get the biggest current. So like if I shoot 5, I will get the highest current from like channel that is channel number 5, right? And you can see that these are simulations of how this device should work. And here is the measurement, so it's very similar. But in here we have actual neural network, so it's quite similar like here, but you have nonlinear function at the output, and the simulated fill factors were slightly different. You can see it's quite bad, especially 9 is, I hate to say it, but it's ugly. But it's surprisingly, the predictions was much better than in the previous case. Even though it's harder for the eye, the computer understands it more. And you can see that the differences in currents were much smaller compared to the previous approach. But it's actually good because it means it's more robust to noise. Yeah, and also in here, well, hardware, making hardware is not that easy. Like I know that people are about software, but hardware is very hard. So in this approach, you can't really like change responsivities. So once you create the chip, you can't really change it. And also fill factor cannot be negative, right? Because it's an area ratio. So you can't have weights that are bigger, that are smaller than 0. In this scenario, you couldn't add any bias. Maybe that's why it wasn't that pretty. But it still did recognize images quite well. Okay, so it's almost the end. Summary. So I like to make this slide. If you didn't remember anything from the talk or you didn't listen, just this slide should be sufficient. So basically, a very basic neural network can be a chip with subpixels when different subpixels represent different weights. Actually, their responsivity represents different weights. Then they are connected, and the current that we measure is actually the matrix multiplication already. So you don't have to do it. You don't have to, create, burn coal, produce carbon dioxide on training, because actually training a normal neural network usually takes like 3 households like use in 3 years. So it's very, very, even the basic one. So it's very, very not energy efficient. This is energy efficient. And it's analog, fast, it's beauty. And actually, I know that also for regular computing, people are doing this analog processors, and it's quite a big thing in Silicon Valley right now, not only for image processing. It doesn't have any latency, so it can, here we measured 50 nanoseconds, but it can be of order of picoseconds. It's scalable, and it worked as a classifier, so it can tell you which letter it is, and it can also recreate letters that are very noisy. And this is the end. Thank you so much for listening to my talk.
Thanks. So any questions, comments? Oh no, so I have a question. So is this the chip designed for the specific domain?
What do you mean by domain?
I mean, the domain means purpose. Okay.
Yes, so it's a specific purpose of projecting letters that are monochromatic. But my understanding is that further engineering can be that you can add like color sensitivities, because different materials have absorption in different colors. So you can modify it as well. So it's like a proof of concept that opens the doors for further research. And this is a basic research conference, right? So it is very basic, but it's not just for this domain. It can be, adjust for really anything you want. It's just a matter of engineering and trying to make, small connections and find right materials that can be, modulated in a specific ways, etc.
Okay, so what's the potential practical application?
So the chip sees the image and it understands right away what it is, right? You don't have to take a picture with the camera, then put filters, then change the image. It should understand what it sees right away.
So the chip is designed to replace the electric unit.
Yes, but without the bottleneck of like going back and forth memory. But basically, you get the matrix products just by measuring current, and it's given to you by nature. You don't have to multiply anything.
Okay. So, any other questions? Okay, please.
The device can integrate with the transformer structure.
What kind of transformers?
The transformers architecture.
Sorry?
Transformer architecture.
Yes, so actually, as you can see, it is integrated, right? So we did part of the work on the chip and part of the work on the computer, right? So in here in blue, no, not in here, is what is done by the computer. And in white, it's what's done by the computer, and in blue, what's done by the chip. So it has a direct connection, but also, as you can see here, in here, basically the chip gives you the response that is binary. So basically it's already a connection. You have something that is, an image, and it has, different intensities, etc. It has analog actually intensity because it can be any, power, but it can compress it. It can do binary hashing to the image. So fast. I don't know if that answers your question or not. You can ask again.
Okay.
Because I'm not sure which transformer you mean. I don't know, Dima, you have any ideas? Yeah. Because you can transform a lot of different things to different things, right?
Because transformer is a kind of neural network.
Ah, okay.
But it's not a little different from the full connected neural network, because it is full connected, but
Yeah.
transformer is not full connected.
So what does it take as an input, this transformer neural network?
You know the transformer architecture.
I don't, sadly.
Transformer.
Yes, yeah, I know, but I don't know exactly how this structure looks like. But yeah, it depends what input it takes, right? If it takes binary input, if it takes analog input.
What about the?
Because you can have both analog input, kind of, right? Because you can have different currents that are continuous. You can do the binary hashing. And I don't know what's the purpose of transforming neural network. You said it's partly disconnected, but what's the purpose of it? Sadly, I'm not familiar, but I'm trying to guess. I mean, I'm trying to do like an educated guess, or like.
Thank you.
No worries.
Okay. Any other questions? Okay.
The online function in the neural network is how to realize in the chip.
What? Sorry?
The online function, just like ReLU, and the softmax is how to realize in the chip.
Okay. So it's actually not in the chip, it's done on the computer. So we have currents, and we add some bias on the chip, because you can, so bias is added on the chip, But then the softmax function, for example, it's actually done on the computer already. So you have like in here. So we have currents, and then, well, we go to the PC to apply the softmax function.
It is realized in PC, not on the.
Yeah, not on chip. So
Okay.
the function itself is implemented on the PC.
So summarization can be realized on the chip.
Yes. So summation and like multiplication.
Okay.
Yeah. But I think technically you could add non-linearity, right? Because it's mixing different signals, right? So you have a certain signal and maybe you can, modulate it somehow to get the softmax function. Mm-hmm. Okay. Mm-hmm. Well, it's also implemented on the PC, but from my knowledge of electrical engineering, you can do it, right? You can mix like different waves, right? And then you could like basically do it on the chip, but we didn't do it because it's adds another layer of complication, right? You would have to mix different signals. Yeah.
Any other questions? No, none. Okay, so thank the speaker again.
Thank you for your questions. They were very nice.
And thank you for the other three speakers, and thank you for your coming. Okay, it's over.